Hi class. So you have a lab this week of a carbonate analysis, molar volume of carbon dioxide. This is a lab that we do in person and it's a pretty fast lab. It's the prep takes about 30 to 40 minutes and the lab itself, the experiment's about 3 minutes, 3 to 5 minutes. So prep takes longer than the lab and that's what most students hate about it. The second trial is not usually as bad once they understand how they have to set it up, and then it goes pretty fast after that. So let's get started. So the objectives of this, you should always look at the objectives. I realize that we're not inside the lab to do this, but if you add, when you write up your lab, these are what you would be giving me in your conclusion. You're going to determine the percent of calcium carbonate in the mixture, and you're going to determine the molar volume of CO2 at STP conditions. Everybody's will be different normally if you were in the lab, which kind of disturbs some people because they have a whole bunch of water displaced and then others have very little water displaced and they have a hard time with this. They always think they did something wrong, but based on the percentage of CO2, that's what's going to basically determine how much of this is going to be pushed out of the graduate cylinder. This experiment, you're going to collect gas by displacement of water. The gas is just going to push the water out of the graduated cylinder, and then we're going to measure it, or you're going to measure it. So STP and molar volume, standard temperature and pressure. Pressure is 1 atm, 760 millimeter mercury, 760 torr, and the temperature is Kelvin, 273.15 or 0 degrees Celsius. So an example is if you had 1 mole of a gas at 1 atm at 0 degrees Celsius, what would the volume be? So when you plug all these in with the gas constant, it actually comes out to 22.4. This is our molar volume for a gas, and that's what it's called here. I showed it here. 22.4, it's liters per mole. That is 1 mole of any gas at STP will equal 22.4 liters per mole. What this basically means that 1 mole occupies this volume, 22.4, and we're going to end up using that today. Molar volume. A mole contains 6.022 times 10 to 23 molecules. We should all know that's Avogadro's number. It's a lot easier just to explain it if you look down here. There's different gases. They all have different molar masses. However, at 1 mole, they are all have the same amount of molecules. And with the if you look at standard temperature and pressure, that means that their molar volume, regardless, will be 22.4 liters per mole. And I have a nice little box that explains this here. It's important to recognize that 1 mole measures different gases at different masses, have different masses, even though they all have the same volume. And there's a nice little conversion here that if you had to use this, you should know that this is what that means. 22.4 liters is 1 mole, and you can flip that. Just another little picture so you can see that these are all at 22.4 liters, 1 atm, 273, 1 mole, and their masses are all different. In this lab, you're going to be using the combined gas law. If you look, this has pressure, volume, and temperature in one conditions, and pressure, volume, and temperature in another conditions. There is no change in number of moles, so when you're doing this, moles are not going to come into this until later. We have the concept that the moles do not change with this reaction. That may not make sense right now, but this is a combined gas law. Moles aren't involved. All right, these are my own words on this lab and how it is how you're going to go through it. You definitely should read the instructions. I'm sure Entis has a whole bunch of questions on the lab and you don't want to miss it. Do not ever blame me because I am telling you right now, I'm putting this in my own words. He might ask for some stuff. So the first thing you need to know is what the generator is. The generator is what throws people off because you think of an electric generator. This is in terms, it's generating CO2, so that's why it's called a generator. So if you look at this first box, and I took this all from the lab. Like I said, this is a lab that we do in person. There's a tiny little test tube, and then there's a bigger test tube, and it's in a beaker. The beaker is not involved in this lab. It is simply holding the test tube up. So what you see is gray. That's the HCl. And in this tiny little test tube is your sample of calcium carbonate, which is a mixture. You have a mixture in here. Everybody has different percent. And they are separated from each other. This is the generator. What's going to happen? This is the HCl is going to, you're going to mix this, you're going to shake this. And when you shake it, it's going to push the reaction out of the inlet. So if we jump over this one, see it's a CO2 gas generator. So you're going to stopper it really tight without breaking the glass. I've had that happen, and I've also had the stopper not on tight and HCl spilled everywhere. So these things happen. You would stopper this as tight as you can. There's an inlet, so there's a hole in this stopper, and there's this glass tube that connects to a rubber hose. So when you shake this, it's going to shake up and down, and it's going to force these two substances to react, which is going to generate CO2. The tube is, as you can see, if this was to be on this side, it would go into, you would have a larger beaker to do this in. And this is why it takes so long of prep, long time for most students, because it's really hard to get this done. So you have this rubber tube that has another little glass inlet or tube outlet, whatever you want to call this. And you stick it underneath the grad cylinder. And the grad cylinder, as you can see, is held in place. Now, the problem with this is none of these pictures show that the water has to be completely to the top with no air bubbles. If you have air bubbles, the answer is going to be wrong. You are already having bubbles or gas in place where water should be. So there's already a displacement, which you cannot have. That's the hard part. Everybody can do this. Everybody can flip this over with water, and it'll probably end up here. To get this to flip with this O filled with water and leave it at the top is the hardest part. And it has to have no volume of gas at the top. So that's what this takes. Students get pretty skilled at it after a while. So then you have it placed in water. And it just has to be 2/3. The volume of the water in this one does not matter. So what happens is that when you shake this, it's going to force the CO2. The CO2 is going to come through here and push out the water. And that's what you see in this picture here, is that this is going to go through water. This is why you saturate the outside water with Alka-Seltzer, because of the fact that the Alka-Seltzer, the water can take up CO2, which you do not want. You want from your reaction to be completely accounted for. So you saturate the water with Alka-Seltzer to prevent any more CO2 being taken in by the water. So this is going through the water, and eventually you see this volume is being pushed down until this is an exaggeration. I've never seen it like this. It's usually like this for most students, and then for some of the students that are really sad, because I'll explain to you why this is when they have it like up to here, it's not really good. So because this part will tell you why when they have it up to here and the change of volume is not much, that makes this a lot harder. So it's usually up to here, but we consider this wet CO2 because it had to go through the water in order for this to be pushed out. So even though it's saturated, there is still water droplets in here, water, and it's taking up water pressure we have to account for. The last step is the one that a lot of students don't understand. Let's say that this is where your volume ended. This is not the volume you're collecting. You need to equilibrate the pressure that is in here with the pressure outside in the environment or outside in the beaker. So the volume, you have to very carefully release this enough, move this up and down until the volume on the inside of the beaker matches the volume of the outside, and that's what you collect. And then this is also when you take the pressure of everything, because now what's pressure on the inside is equal to the pressure on the outside. This is hard when you have a very small volume. You have to stick your hand in this large tube. There's another graduated cylinder you move this to, and you get your arm wet all the way up to your elbow. It's really fun for some students. You can ask them. So this is my words to explain this lab. Again, you definitely should read this lab over to make sure that you completely understand, but this is a good preview to explain how this lab goes. All right, so here is my little diagram that looks very confusing, but it's the steps that you're actually going to take here. So here is the equation that's given to you in your book. This is calcium carbonate, this is an acid, and it is an excess. So we really don't care about that. As long as it is in excess, it's going to be generated as much CO2 as we can, and that's all we are concerned with. So what happens is that you have your sample, and that is what is in here. But the final is the CO2 that's here. This is what we're interested in. Or actually, I should say this one. Okay. Once we determine the amount of CO2 that has been collected, and you do that by first you determine your sample by weighing your weighing boat and sample and so forth on this one. But this one is the generator. You weigh the generator before the reaction and after the reaction. And the before will be more than the after because the loss of CO2, that is the mass of CO2 that you're collecting. So you will collect that and then you will determine your moles of CO2. This is a 1-to-1 ratio. We're not worried about the HCl. We are worried about the calcium carbonate. This is a 1-to-1 ratio, which means that whatever my moles of this are, it is now my moles of this. I can get my mass of this, and I have my sample mass, set those up, I can determine my mass of calcium carbonate. We are also doing another step where we have to determine the molar volume. So there's a few steps we have to do in here. So I pulled out the equations that you're going to need for this lab. There's other little things you have to do, but these are the main ones. And you can see once you determine the pressure of the CO2 that's dry, meaning you remove the water pressure, you are going to plug it into the combined gas law. This combined gas law has the STP conditions, and then the ones that are not filled in are your experimental conditions to find out the volume of STP in STP conditions. Now, because this is a real gas, it's not going to match completely with the gas of 22.4. That's an ideal gas law. That's an ideal gas. Ideal gases do not exist, but we're going to force it into conditions to see what number we come up with. So don't be worried if the volume of gas does not match 22.4. It's not going to because it's a real gas. Then, as you can see, the red is what the steps are. Once you get this one, you can now determine your volume because you'll know your moles of CO2. Then, once you know your moles of CO2, you can determine your moles of calcium carbonate, your mass of calcium carbonate, and you already know what your sample mixture is. And that's going to give you your mass, your percent of calcium carbonate in the sample. I don't know if he gave you pre-lab or not, but if you had problems, this is the one you should work on to understand it. Okay, so I made up some data. Does not match anything Antis gave you, hopefully. And but I did try to match his table. So this is what it kind of looks like. You have your weighing boat, in the sample, your generator before anything happens and after. So you see that this one is more than that one. This difference is the CO2. You have your graduated cylinder, and then you have your temperature of the water, which you need because you're going to have to figure out the pressure. So I already put that information here because in the back of the book is an appendix, and you'll look at the temperature of the water, and that's going to give you a value. But I've already pulled it out here, and this should give you something like that based on the temperature of the water. You can then pull out the temperature of the water in a value. And then I'm saying that this is the atmospheric pressure right here. Okay. So the first thing you can do is determine the sample amount. This isn't too bad. These steps should be okay to understand. This is your weighing boat. This is your weighing boat and sample. You determine what your sample is of your mixture of calcium carbonate. Then you determine your mass of CO2 generated. These are the generators. This is your, if I did this right, this is my initial minus my final. Yes, it probably should be the other way around, but we don't work with negative numbers here. And I already told you that the mass loss is the CO2. So this is kind of weird that you're using the initial minus the final, but we don't work with negatives. So that's how you're doing that one. Then we need to determine the dry pressure of CO2. The dry pressure of CO2 is removing the water. So we have gas that has been collected in here, and you can kind of see that this level means the atmosphere, this is even. But in here, you also have pressure of CO2 and water. We need to remove that in order to determine what is the pressure of the dry CO2. So I put this information on the other slide. You can always refer back to that. And here's the equation. You have P total equals pressure of CO2 plus pressure of water. We are going to change that around to determine what the pressure of dry is. And I take my atmospheric barometric pressure minus the water, and it gives me my answer. Next step, you're going to convert the volume of CO2 collected, which is simply changing from milliliters to liters. We don't work with milliliters when we're doing combined gas law and so forth. And then the temperature of the CO2, which is the water, because that's where the reaction took place. So we're going to have that as well. We are trying to determine, these are our experimental conditions that we are going to plug into the combined gas law. So here's our data. This is everything that I collected from that page. This is the data that we're going to plug into our combined gas law. So there are already some numbers here. These are STP conditions. We do not have the STP conditions for this gas. If it was under ideal conditions, everything for an ideal gas law, it's 22.4. This is a raw gas. It's not going to oh, sorry, no, this is molar volume. Forget it. Forget I said that. This is volume. I'm getting one step ahead, and I'll repeat that when we get to that equation. We don't have this one right here. So let's plug this in. So we have our pressure that's dry. That's going to go there. We have our volume of CO2. That's going to go there. And we have our temperature. That's going to go there. And there are STP conditions. We plug this all in. It should be in liters. And this is under STP conditions with our experimental conditions. We determine what the actual volume is. And it is different, if you can see, from what the volume was in with our experimental conditions. Now, the next thing is determine our molar volume, which is exactly what I was jumping ahead to. For 1 mole of CO2. Now, this is a raw gas, so it's not going to match the 22.4. It's going to have its own value, but it should be somewhere in that range, regardless of it. So we have our grams of our mass of CO2 generated, and then we're going to simply do stoichiometry to determine our moles of CO2. So this is not difficult to do. My picture may be a little confusing, but once you understand the steps, if you look at it, it actually makes a little bit more sense, hopefully. Then we're going to plug it into this equation, which I did here. And for my mass, my molar volume of CO2, it's 19.88 liters per mole, which is exactly what I told you, would not match the 22.4? I'm even forgetting myself now. And the last step is to determine the percent. I took this straight out of the PDF that you were given. Now I have CO2 moles of a value here. And my sample is here. So this is what I weighed out before the reaction, this one in the little test tube. I need to determine my mass. So I'm going to take my moles of CO2. You can see that this is a 1-to-1 ratio. So that simply means that whatever my moles of CO2 are, they are now my moles of calcium carbonate. Do stoichiometry, I now have my mass of calcium carbonate. Plug it into this equation. I have a 63.41% calcium carbonate in the sample. This is not a difficult lab. If you were in person, you would probably be, there's about 75%, no, there's probably more. 85% of the class is really irritated with the first trial because it really takes 40 minutes is usually what it takes to everybody get it to where they can do the first trial. And then the second one, pretty fast. But I think it's even more annoying for students because this literally takes 5 minutes. This reaction is 5 minutes long and it's 40 minutes of prep. But it's actually not a bad lab. I like this lab. It's not a difficult lab. It's pretty easy. And even though these steps seem like they may be a lot, they're really nothing that you guys have not already handled. You can handle this very well. What could go wrong? So I just left the slide in. This is for my class. Reading the graduated cylinder wrong, you're reading it upside down. So it is a little hard to understand. Small bubbles in the graduated cylinder. So if you don't remove all the bubbles, same as in the titration, you're already losing volume. It's to something else, and it should be to whatever you're working on. And that's sometimes what happens. When you try to flip it, you get it perfect at the top, and then there's a little bubble. You have to just realize, is it worth the cost of fixing it or not? Small amount of other gases from the atmosphere dissolve in the water. That's very small, but it can happen. And the water is not completely saturated with CO2. So what you do is you have I think it's half a tablet or a tablet, and you have to saturate it. So if we were to use this, it would be completely saturated. It takes time to saturate, and students want to get in, want to get out. Even though I don't let them go early, they try their best. And so they might make, and I've seen it happen, they will do this reaction without the CO2 being saturated from the Alka-Seltzer, which means that they lose volume from the reaction because it goes into the water and we can't determine that. So the Alka-Seltzer has to be completely dissolved, and that way you know that it's been saturated, and the CO2 that you're collecting is going to be as correct as possible because it's not going to go into the water. So that's some of the problems here. And that's about it with it. Besides I had a student that lost the stopper in the middle of this reaction and HCl went all over and they had to clean everything and start over. That's the fun parts of chemistry. And that's it. The lab is over. So hopefully you understood this and this helps you finish this lab.